Welcome to the fifth lecture video in our Class 12 time series of lecture videos. At the end of our fourth lecture video, we were discussing a scenario about whether, what if you start with something that's optically active in terms of your radical halogenation starting material. So here we've got R2-bromobutane. That's a pure enantiomer. It's optically active. And we discovered, 5 and 6 are enantiomers. We would expect the relative amounts of 5 and 6 to be equal 1 to 1. We said, compounds 1 and 2 were constitutional isomers. They aren't really stereoisomers. However, compounds 3 and 4 are stereoisomers. They're molecules whose atoms have the same connectivity but a different orientation in space, and so we had to decide how do you classify the RR and the SR, and they are diastereomers. And so we'll move forward with what do we think about 3 and 4? Well, how were they constructed? Our radical chlorine abstracted a hydrogen from this secondary carbon and created a radical, and now chlorine has to come in and react with that radical. So what does that look like? Well, what about the relative amounts of 3 and 4? Like I said, our chlorine radical came in and abstracted one of these two hydrogens from this carbon and created this radical. Now this radical is actually chiral. It's not achiral. Why is it chiral? Because it possesses one stereocenter. And now the chlorine has a choice. It could come in from the top lobe or the bottom lobe, but now that is not energetically the same. Why? Because the transition states have a diastereotopic sort of look to them. So if our chlorine comes in from the top, we get 3. If our chlorine comes in from the bottom, we get 4. In this scenario. Since 3 and 4 are diastereomers, the transition states leading to 3 and 4 are diastereotopic or diastereomeric. They look like they're diastereomers. And so, of course, diastereomers have different physical properties. And so you would expect transition states that look like diastereomers to have different physical properties, including energy. And so, we might say that the transition state leading to compound 3 is higher than the transition state leading to compound 4. We just don't know. It's all theoretical. I wouldn't expect you to know sitting on your own in a corner. However, there is one experimental case that we do know, and we'll look at that shortly. Diastereomeric transition states can have completely different energies, so we would expect 3 and 4 might be formed at different rates. Even if 3 is thermodynamically more stable than 4, it might not be formed as fast, especially if the reaction is not reversible. It is difficult to predict. So, in the hypothetical energy diagram, even though 3 is lower in energy than 4, the activation energy leading to compound 3, that is the transition state 3, height is higher than transition state 4. So 4 you would expect to be formed faster. We're already on page 79 of notes. I guess we're making great progress. So, one case that is experimentally known is the bromination of trans 1,2-dimethyl cyclopentane. So here we have trans 1,2-dimethyl cyclopentane. We're going to expose it to bromine and light. So radical bromination is selective for tertiary hydrogen abstraction. So we have, our methyl groups are primary hydrogens, these are secondary carbons, so they have secondary hydrogens, but we've got a couple of tertiary hydrogens. We're highly selective for those, so we're going to take one or the other, and lo and behold, if we take this one, we end up with this type of radical, This methyl group we might expect to be in the same plane as our 5-membered ring. Now bromine has to make a choice whether it comes in from the top or the bottom lobe, and on the top it has to contend with a methyl group adjacent to it. From the bottom it has to contend with a hydrogen, so sterically it's going to be less favorable to come in from the top. We don't form this particular molecule, which would be from bromine coming in from that top lobe. Our major isomer, stereoisomer, is from bromine coming in to the bottom lobe. So your major isomers are where the methyl groups are end up on the same side of the ring. Oh wow. And we would expect an equal amount of this compound's enantiomer. And I'll let you guys figure out where that comes from. So I will see you at the class 12 time session.